In this video, we're going to look at the centers of mass of various different shapes, some composite laminas, and also wire frameworks. To start with, we will look at this lamina, A, B, C, D, E, which is formed of a rectangle and an isosceles triangle. What do we think we know about the center of mass? Well, firstly, it's symmetrical about the green line. So we would expect the center of mass to lie on this line of symmetry. Let's have a blue pen. So the center of mass will lie on the line of symmetry. Which is the green line in the diagram. When looking for the center of mass of a composite figure, you should always split the figure up into some easy shapes: rectangle, isosceles triangle, and the combined figure. I expect to see this diagram or equivalent for the solution of every question. It helps you to stay under control, and it makes it much easier for the person who's reading it to see what's going on. Well, firstly, let's look at the rectangle. We would expect the mass of the rectangle to be concentrated at its center of mass. That is what we've been looking at in other videos. So if we look at the center of mass here, let's call it G1, that will be a distance of 4 from the line AB, half of 8. So we can think of the rectangle as all concentrated at the point G1, so all the mass is just there. Let's look at the triangle. What do we remember about a triangle? Center of mass. The center of mass is 1/3 of the way from the base along a median. Well, the median is of length 6, 1/3 of the way, therefore, will be of length 2. So let's call the center of mass G2, and it is at a distance of 2 from the base of the triangle. In the combined figure, well, we would expect the center of mass of the combined figure to be somewhere a little beyond halfway in the rectangle. Somewhere about there seems fairly sensible. So let's put G here, and let's suppose that that is a distance of x bar from the line AB. We're now in a position to find the position of the center of mass. We want the mass of each of these shapes. The mass is going to be proportional to the area. Uniform lamina, therefore, if something is twice the area, it will be twice the mass. So we can actually take the area and think of that as the mass. Let's take the area of the rectangle is 4 times 8, which is 32. Of the triangle is a half base times height. That's a half times 4 times 6, that's 12. And the area of the whole figure must be 32 plus 12, which is 44. Now we want to know the distance x measured from AB. For the rectangle, we're thinking of all the mass at G1, and its distance xi from AB is 4. For the triangle, we are 2 from the base of the triangle, so the distance from AB is 8 plus 2. So the distance is 10. And for the combined figure, we've said that the distance is x bar. That is the number we're looking for. Now let's look at sigma mixi is equal to mx bar. That's the same as x bar equals sigma mixi over m. Well, the area is the mi, the distance is 4. 32 times 4 is 128. For the triangle, 10 times 12, mixi is 120. And for the combined figure, we have 44 x bar. So we are taking the rectangle and adding the triangle, sigma mixi, and that is giving us the combined shape. This now gives us 248. Divide by 44, and we'll get x bar is 248 over 44, which is 5 7/11. Or do we think that's sensible? 4 would be the midpoint of the rectangle. 5 7/11 is a bit further. Yeah, I reckon that's okay. I'm happy with that. And so the center of mass is on the line of symmetry at a distance of 5 7/11 from the line AB. If you can hear a noise in the background, that's my washing machine. Now let's look at another problem. In this one, we have another uniform lamina, shape of a rectangle from which a semicircle has been removed. Well, let's just remind ourselves of one result. And that is the formula for the position of the center of mass of a sector. The formula that we have is that OG is equal to 2r sine alpha over 3 alpha. Well, in this case, we have a circle whose radius is half of 6, radius is 3, and remember that alpha is only half of the angle at the center. The angle alpha is pi by 2. So this formula gives us 2 times 3 sine pi by 2 is 1 divided by 3 pi by 2, and that is 4 over pi. And so in this particular case, we know that the center of mass of the semicircle is 4 over pi from O. We shall be using that result in a moment. Once again, we draw separate figures. We draw the rectangle, we draw the semicircle, and we draw the composite figure. Now you could think of this figure plus the semicircle being the rectangle, but I think it's easier in this case to think of the rectangle, take away the semicircle, and give us the composite figure. So this would give us the rectangle, take away the semicircle, and we end up with the composite figure. In the same way as before, let's think of all the mass of the rectangle as concentrated at its center of mass, which I'll call G1. This time I'm going to measure all the distances from O. So if the length of AD is 8, then OG1 is just going to be 4. With the semicircle, the center of mass is going to be at G2, and we've just worked out, although it's magically disappeared, that the length of OG2 is 4 divided by pi. And for the combined figure, well, where do we think the center of mass is going to be? If it was the rectangle, it would be in the middle. We've taken a bite out. We're going to have moved the center of mass somewhere roughly where this arrow is pointing now. So let's put a little marker for the center of mass, G, and that is going to be a distance of x bar from O. Okay. Let's give myself a little bit more space down below. I'm going to do the same as before. The area we can think of as the mass. The area of 6 by 8 rectangle is 48. The area of the circle is a half pi r squared. Well, the radius is 3. Pi r squared is 9 pi, so that is 9 pi, half of the area of the circle. And that means that this is 48, which is 96 over 2, minus 9 pi. So that's 48 minus 9 pi by 2. This time we're going to measure xi from O. And we'll take towards the left as being positive. This gives us that xi for the rectangle is 4. Xi for the semicircle is 4 over pi. And xi for the combined figure is x bar. Now we do sigma mi xi is mx bar. 4 times 48 is 192. Now this time we're going to subtract mi/xi. If we look at that, 9 pi over 2 times 4 pi, the pi's cancel. 9 times 4 is 36 over 2 is 18. And that equals 96 minus 9 pi over over 2 times x bar. 192 minus 18 is 174. So x bar is going to be 174 times 2 over 96 minus 9 pi. That, to 3 significant figures, is 5.14. Well, do we think that looks sensible? Remember, we're measuring from O. The whole of the length is 8. Halfway, 5.14. Yes, I think 5.14. It's not stupid anyway. So we'll be happy with 5.14. Therefore, my center of mass again lies on the line of symmetry. And it is a distance of 5.14 from O. Now we look at something a little bit different. This time, instead of having a lamina, we've got a wire framework. In other words, there is nothing in the middle here. We just have a wire or a rod, another wire, another wire, and another wire. And we have right angles there and there. Not said so in the question, but that is the case. And we want to find the center of mass of that wire framework. Well, we shall need the length of DC. So let's have a little look at trying to get that. If we take a line straight down from D to the bottom, let's just move it a little bit. Then the length of the line from D to the bottom is 8. The line from, let's call it E to C, will be 6, 16 minus 10. And if you know your Pythagoras, you will have realized that we have 10, 6, 8, 10 for a Pythagoras triangle. So let's get rid of the bits that we don't want. And we now have a framework where we know all the lengths of the lines. Well, when we have a wire framework, we can think of each wire, the mass of each wire, as concentrated at its midpoint. So if we concentrate the mass of the first wire at its midpoint, the second wire at its midpoint, the third one, and the fourth one. Then the length of the wire this time is going to correspond to the mass. If a wire is twice as long as another one, it will be twice as heavy. So we have the wire AB has mass 8, and we can think of it as a particle at its midpoint. Well, in this case, it's very often easier to think of having coordinates. So let's assume, or let's take the origin at B. If we take the origin at B, then sigma mi ri is equal to, divided by the big M, is equal to r center of mass. So we want sigma mi ri divided by the total mass, and we will have the position of the center of mass. R bar is equal to, well, let's take AB for starters. That is 8 times halfway up 0.4. Let's take BC. BC will be 16 times 8 naught. What about AB? AB is 5 away from B and 8 up. So that is 10 times 5, 8. And now we want to know where the central point of DC is. Not such a good line this time. The distance from E as it was to C was 6, so that is 3. So the x-coordinate of the midpoint, the x-coordinate of this point is going to be 10 plus 3 is 13, and the y-coordinate is going to be halfway up, which is 4. So that is a mass of 10 at the point where x is 13 and y is 4. Let's make that 3 a little nicer. Haha, didn't work. Better. Now we divide by the total mass, and that is 8 plus 16 plus 10 plus 10. Working out the top line, we get 308, wasn't that quick, divided, or not divided by, and 152. divided by 44. And that is 7 3 5/11. So there is the position of our centre of mass for the wire framework. 7 3 5/11. So 7 along, it's not areas we're looking at this time, and 3 5/11 upwards. I'm fairly happy with that. I got more wire below than I have above, so I'm expecting to be below halfway, and I've got more wire out. Yes, I think that all seems fairly sensible. You can find out more about composite figures and wire frameworks in your textbook M2 from pages 44 to 48. So if you look in your textbook M2 pages 44 to 48, you will find out more about this topic.